Okay, welcome to part 2 of our probability class. Okay. Use the spinner at right to determine the following probabilities. First of all, you need to know that we read that P of A. That means the probability of landing on A. So what we know is we know that A is 90 degrees. That angle is 90 degrees. Okay, so we know that if that angle is 90 degrees, that is actually 90. Can't see that very well. 90 out of a possible 360 degrees, right? And 90 out of 360 is the same as 1 out of 4, which means that we are basically saying that the part of the spinner that is A is actually 1/4 of the entire circle, which means P of A is 1/4. Probability of landing on A is 1/4. What about the probability of landing on A or C? Okay. Well, if A is 90 degrees and C is 60 degrees, together they are 150 degrees. So the probability of landing on A or C is going to be 150 out of a possible 360 degrees, which is the same as 5 out of 12. Okay. Now the probability of D we're going to have to find. We know that A plus B plus C is the same as 90 plus 40 plus 60 degrees, which is the same as a 190 degrees. Which means probability of D is going to be not getting 190 degrees. So we had 190 covered with everything but D. So if we take that 190 that's A, B, and C away, we get 170, which means D is 170 degrees. Which means that the probability of D is 170 out of 360, which is the same as 17 out of 36. And the probability of E, well, that's easy. Probability of E is there any on the board? No, there's not. There is absolutely no chance that we're going to spin that spinner and land on E. So the probability of E is 0. Okay, we've got this spinner, and it looks like it's divided into 6 sections, and we spun the spinner 100 times. Based on the fact that we got 49, we landed on red 49 times. We landed on yellow 36 times, and we landed on blue 15 times when we spun the spinner 100 times. How do you think the spinner was actually colored? Well, if we spun the spinner and got 49 reds out of 100 spins, that's pretty darn close to half. That's pretty darn close to 50%. 49 out of 100 is 49%, which is very, very close to 50%. If we got 36 yellow out of 100, well, that's 36% right there. That's a little more than a third. Okay, so what I'm looking at here is I'm looking at coloring a third of this yellow and half of it red. Which leaves 1/6 of it to be blue. Okay, what about this dartboard? I want to know what the probability is going to be of hitting the shaded region with the dart. That means I've got to know what the area is of that shaded region, and I've also got to know the area of the entire board. Let's start with the area of the entire board because I think that's going to be really quick to find. We know that the radius of the large circle is, let's see, 3 inches. And we know how to find the area of a circle, that's pi r squared. So in this case, the area of the entire dartboard is pi times 3 squared, which is 9 pi. Okay. Now let's find the area of this medium circle right here. It's not the shaded area, it's the shaded area plus some in the middle. Let's find the area of that. We know the radius, it tells us. The radius is 2 inches, which means for the medium circle, it's pi times 2 squared, which is 4 pi. Okay. The first one we took was the whole board. The whole dartboard is 9 pi inches, square inches. Just that medium circle there is 4 pi. Okay, and now we've got to take this medium circle, and to find the shaded area, we're going to need to actually take this medium circle and we're going to need to subtract. We've got to subtract that. Let's subtract that green part there. That's the small circle. The radius of that small circle is 1. So the area of the small circle is pi. Because 1 squared is 1. Or 1 pi, we could call it 1 pi. Okay, so to find the shaded area, we're going to take the medium circle, 4 pi, and we're going to subtract the small circle, 1 pi, which gives us an area of 3 pi. So now we know that the area of the whole board is 9 pi, and the area that's shaded is 3 pi. Which means the probability of landing in the shaded area, let's just say P. P of shaded area. The probability of landing in the shaded area is the area is 3 pi out of a total possible area of 9 pi, which is 1/3. The probability is 1/3. Let's talk about when events are mutually exclusive. Sometimes we also say disjoint. Okay. 2 events are mutually exclusive if they have no outcomes in common. For example, if I were talking about sitting in my car right now and sitting at my desk here at the same time, we know that's impossible. I am not both sitting in my car and sitting at my desk. Those two things, sitting in my car and sitting at my desk, are mutually exclusive. That means they cannot exist at the same time. Those two things are mutually exclusive. Which means the probability of me sitting in my car and sitting at my desk at the same time is 0. There is no probability of that happening. Now, something that's not mutually exclusive, having blonde hair and brown eyes. If somebody asked you, do you have blonde hair or brown eyes? You would kind of look at them funny because you would say, well, those aren't mutually exclusive. I can have both. Brown hair and brown eyes and blonde hair are not mutually exclusive. You can have them both at the same time. This is a problem about someone who wants to know if catching a cold happens more frequently when you don't get enough sleep. So what we've done is we've made a two-way table to explain after she asked her 30 students to keep track of her numbers. So I've gone ahead and I've basically recreated this two-way table on this piece of paper so that I can total it up. Okay, the total number of students is 30. That includes the 20 that got less than 8 hours of sleep and the 10 that got 8 hours of sleep or more. That 30 includes the 24 that caught colds and the 6 that didn't catch a cold. So what is the probability that a randomly chosen student has caught a cold out of all the students that were surveyed here? Okay, which is a total of 30 students. What is the probability that one of those students caught a cold? Well, how many students caught a cold? 24 students caught a cold, which means the probability is 4/5, 4 out of 5, or 80%. Now, what is the probability that a student that didn't get enough sleep caught a cold? Well, how many students didn't get enough sleep? 20 students didn't get enough sleep. Out of those 20, how many caught a cold? 16 caught a cold according to our two-way table, which is 4/5. Now this is telling. 4/5 of all the students caught a cold, and 4/5 of the students who got not enough sleep caught a cold. What we're talking about here is independent events. What she's trying to find out is catching a cold independent of the amount of sleep you get? Or does catching a cold depend on how much sleep you get? If the outcome of a probabilistic event does not affect the probability of another event, then the events are independent. For example, if I flip a coin and I get heads, and then I hand the coin to you and you flip the coin, if I said, you're more likely to get heads now because I flipped it and got heads, you would know that doesn't make any sense. Because those two coin flips are independent events. Your coin flip does not depend on what my coin flip was. My coin flip is not affecting your coin flip at all, which means those are independent events. So the question here is catching a cold independent of sleep? Well, catching a cold 4/5 of the time, whether you've got enough sleep or not, pretty much says that the probability of catching a cold does not increase if you lose sleep. So catching a cold is independent of losing sleep. I hope that helped you deal with probability a little bit. We'll see you next class.